look at it. Log 2 is 0.3. Next step. In 5 minutes I will finish this lecture, but you should understand this point. That means, if I say that the absorbance at this particular wavelength, let me say I have chosen the wavelength 400 nanometer. Absorbance at 400 nanometer is 0.32, means automatically I will understand that 50 photons came here, 40 photons only came out, same 50 photons came, only 20 photons came out. Understand? Because 40 by 20 only can give me 0.32. So that means this particular dye is capable of absorbing 50% of the photons that are coming in. Understand?
We will find the absorption for the 400 or for the dye?
Absorption for the dye at 400.
At 400.
Absorption for the dye at 400 nanometer.
When we send 400 through dye?
Through the dye. Understand? Next step. I have measured the absorption at 400 nanometer. In another wavelength it may be more or less, I don't know. So what I can do, look at it, very simple. I rotate the grating. Then instead of 400 I can go
take
to
600,
500. 500. I do the same experiment. Then I match all of them, then I put the mold together, put in the form of a graph. This is 0.32, this is 0.8, this is 0.6, something like this one. This is 400, this is 600 nanometer.
But if we get one, like 0.32,
You can get.
we can calculate other without experiment?
Without the experiment, how can you do this?
Calculation. There is no calculation.
You cannot.
We cannot.
You have to do experiment. Now, once I have done this one, I know for this particular dye, 500 nanometer is the maximum absorption. Understand? It will absorb strongly at 500 nanometer.
How can we know the intensity or number of photons by the instrument?
By the instrument, it's all calibrated because 50 comes, we assume whatever it is comes.
But when I use that instrument, I don't know.
No, we don't have to know. That's what I'm saying. I'm giving an example of 50 and 40. 50, 40, 20. It may be 500, it may be 200, we don't care. We need only this. This is something what the instrument measures.
It will appear in the instrument.
Yes, it will appear in the instrument. Next week, we will do this experiment for you.
It's important. We don't know about this. This one, this number.
You should know.
We always do the absorption days and know the wavelength, but we don't care about this one.
No, you would have noted down, but you had forgotten. Anyway, maybe if I have time, I can show you. At least next year, next semester, or sometime later, you tell me what are the experiments you have already done. Because all the instrument which I have here, I can show you someday or another. If not now, next semester.
There is a course called an instrument?
Next semester, instrumentation and laser instrumentation.
Do you,
No, last semester, what did I teach?
Last semester, laser material interaction.
That's a theory, yeah. If it is, I'll be teaching. Instrumentation, I'll be teaching.
you will choose. Okay. We will choose.
Yeah.
I think we will study all instruments,
All instruments.
thermocouples and many things.
Complete.
In the lab, maybe it is.
In the lab. I will take you there. Like mobile repair, we will repair.
Yeah, we need this too.
We need. Only then you will get.
Because sometimes we don't know how can we use thermocouple or some instruments.
next semester, if you take that course,
We'll take it.
if I am taking that course, okay, I know all the instruments here. I will make you to learn every bit. Like I teach car repair, you know, car mechanic. The car
we
mechanic,
need, doctor. We need.
if you go to the car mechanic, the heavy man will kick the paper. Go and do this one.
Yes.
That is why you learn.
Yeah, that's.
That is how we people learn. He will cry, but he will learn. He will shout at him. He will throw the stone at him, but he will learn. He will become another good mechanic. You see that? Okay, don't worry. I will not throw stone. Don't worry. Now come back. Come back to our point. This is all possible, right? This is standard instrument available. Now look at this one. Next up, all the story take place for the molecule from here to here. Okay? In 1 minute you will understand the application of supercontinuum. Suppose I want to find out whether this molecule start absorbing from here to here. I need supercontinuum. Why? The molecule will stay there only for 1 nanosecond.
Before he come down.
Before it comes, I must kick it up, right?
To
what I
using
do-
supercontinuum.
So what I do, you see the instrument, then you will see the beauty. This is what Zoil did. Now look at this. I start with the neodymium laser. 530. Put a lens. You see the schematic, you will understand very well. This is T2O. No, before this. Yes, look at it. I split it. One go. Put it. Here is my sample. Say X. Okay, then here I put the lens, goes through supercontinuum. Then you know what happens? I send this. This is, let me say, 1 nanosecond laser pulse. This laser pulse will kick the molecule up from here to here. Understand? Then look at it. I send the white light supercontinuum coming here. This will come and pass through this one after half nanosecond. Then this molecule will be swept through after half nanosecond. Then I know how many molecules go here, how many molecules has come down. This is called excited state absorption. Excited state absorption. Next interesting thing is, I can adjust the time between this and this. I said half nanosecond. Suppose I send the light after 5 nanoseconds. Then whatever white light I send, it will come straight down because there is no molecule here. They would have come down. Understand? Then immediately I know that this molecule has a maximum lifetime of only 5 nanoseconds here. Understand? On the other hand, if I send it in 1 nanosecond and then the white light becomes weak, supercontinuum weak, that means the molecules here have absorbed and gone elsewhere. That means I can monitor the behavior of molecule in the excited state existing for 1 nanosecond or 2 nanosecond or 1 picosecond also.
How we can control the time?
Very simple, very simple. Look at this one. I send the light here, right? Instead of coming like this, I allow the light to come back.
So we
I can do anything. Or I can quickly push it.
okay.
This is called optical delay line.
Delay
I
line.
can ask it, immediately or come after 1 minute.
Yes, I understand.
Send the right, go and come back. Look, this is all what Zuhail did. What he did, look at it. I want you to give a talk, one of you. What he did, first he took benzene. Anyway, I'm going to finish it. I'm
Okay.
going for this nanomedicine. You can sit down, join anytime. Look at this benzene. If you put bromobenzene, it will have certain absorption. Next step, I add fluorine. Slowly add fluorine. Fluorine is more reactive than bromine, then it will kick this out and become fluorobenzene. Now I can monitor at the rate of every picosecond. Then I know after 10 picosecond, all the bromobenzene have been converted into fluorobenzene. Understand? If I could do that, that means the reaction rate between bromobenzene and fluorobenzene is only 10 picosecond.
So he studied the reaction of
He
the
did
rate of
that. That's all he did. He got Nobel Prize. So this is what you call fast kinetic, or this is called picosecond spectroscopy. He did not only in picosecond, he did even in femtosecond.
he did in 50
Femtosecond. Later, I mean, the same technique, you can do so many other things. You can look for picosecond or even for femtosecond. Okay. Now the point is, I want one of you to give a talk on this, seminar talk. Whatever Zuhail has done. You can give a talk on supercontinuum. You give a talk on applications of supercontinuum. Next week, okay? Right. We have a meeting, good meeting, nanomedicine.
We will go do.
Yeah,